Okay, in this problem, we are given that uh, an aluminum piston of specific gravity 2.64 is moving down in a hollow steel tube, as shown here, with a diameter of 75 mm, the inner diameter of 75 mm, and this piston and the gap between this piston and the steel tube is lubricated using a specific oil given here at a specific temperature so that the viscosity and specific gravity of this oil is can be calculated. So since this this whole assembly is under the action of gravity, the piston will move down due to its own weight, and there will be shear forces acting on the sides of the piston in the opposite direction to its motion. So as a result, after a while, its weight will be balanced by the shear forces acting on the sides of the piston, such that it will attain a terminal velocity. So to attain that terminal velocity, the basically the velocity gradients inside these thin lubrication films will adjust such that the piston weight is exactly balanced by the shear forces acting on the piston. So to solve this problem, let's let's just start with the free body diagram of this piston. So consider this to be the piston. Let's introduce a coordinate system. So the downward direction is Z, and since it is a cylindrical piston, this direction is R, and then we have polar direction theta. But we don't need to worry about theta this problem. The weight of the piston acts in the downward direction, and the shear viscous shear forces on the side of this piston, they act in the upward direction. I will denote them by Fs. So a simple force balance on this piston tells me that in 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 a steady state, or when the piston achieves its terminal velocity, the sum of all the forces acting in the z direction is zero. So since we only have two forces, one is the weight of the piston and the shear forces, we'll get its weight minus Fs to be equal to 0. So now calculating the weight of the piston is easy because we are given the specific gravity of the material, and we are also given the length of the piston and the approximate diameter. So mass is just volume times the density. So mass is specific gravity of aluminium times density of water, pi. Let's say this radius of the piston is capital R, then pi r square L is basically volume, and this is the density of aluminum. So I'll denote this as equation 1. Now, how do we calculate the shear forces acting on the piston? So we are given in the question that the velocity profile within the film can be assumed to be linear. So I'll draw this diagram again. So let's say this is my outer steel tube, this is the piston. Let's say it is moving with a velocity v, and there is a fluid in here. So if I zoom in on this thin film of the fluid, what I'll see is on the left, I will have the side of the piston. On the right, I will have the steel tube, and this piston is moving with a velocity v downwards. So this is moving with a velocity v, and this steel tube is stationary. So because of the no slip boundary condition, the velocity of the fluid near the tube is zero, while the velocity of the fluid which is close to the piston is exactly v. And in between, the velocity varies linearly like this. So this is the radial direction, and let's say the thickness of the film is T. Now we are told in the question to assume the velocity of this thin oil film to be linear. So I can write the z velocity of the fluid film as a function of coordinate r, and it comes out to be v times capital R minus small r divided by t. So here capital R is the radius of the steel tube, and t is the thickness of the oil film between the piston and the outer steel tube. So just to verify, if we substitute R to be equal to capital R, so this gives us the outer steel tube, and the velocity here is basically zero because of the no slip boundary condition. And similarly, if I substitute R equal to capital R minus T, which gives me the piston surface, then I recover UZ R minus T to be equal to capital V. This velocity profile follows the no slip boundary condition. Now, to find out the shear force, we need to first find out the shear stress due to the due to the velocity gradients in the oil film. So essentially, we need to find out the viscous shear stresses tau rz at r equal to r minus t. And again, remember this film thickness T is very small compared to R. And from Newton's law of viscosity, we know that this is related to the viscosity of the oil times the gradient of the gradient of the velocity of the film with respect to the R coordinate. So, or if I focus on a small fluid element in this film, then this is direction R, this is the Z direction. So the shear stress acting on these vertical surfaces by our sign convention, and the convention for notation for the stress, we know that the shear stress act in these direction, and they are denoted by tau rz. So R is basically the surface on which the shear stress is acting. So this is the R surface, and Z is the direction of that stress in which it is acting. So we can find out the gradient of velocity by using the above linear profile. And if you do that. So duz by dr is nothing but minus v by t. And if you substitute it here, you'll get tau rz at r equal to r minus t to be equal to minus v by t will be equal to minus viscosity times v by t, where v by t is this gradient of the z velocity of the oil oil film in the r direction. So this is the expression for the shear stress on a fluid element in the oil film. So the shear stress acting on the piston will be in the opposite direction to this shear stress, and we already know that the shear stress acting on the piston is in the upward direction because it is essentially balancing the downward weight of the piston. So the shear force will be nothing but tau rz at r equal to r minus t. So shear stress acting on the piston surface multiplied by the surface area. And if you the surface area here is basically the surface area of a cylinder, which is given by 2 pi r L. Again, notice that we should be using r minus t for the radius of the cylinder because r is the inner diameter of the steel tube, but since t is very small compared to r minus t is very close to r. So we will just use r for as the radius of the piston as well, and L is the piston length, which is given in the problem. So Fs, the magnitude of Fs is basically the magnitude of this shear stress uh, multiplied by this area. So Fs, that is the shear viscous force acting on the piston, is mu times V divided by T multiplied by 2 pi r L. So now from our force balance, we know that weight minus the shear stress is equal to 0. So basically substituting for mg minus fs, we can find out the unknown v. So mg was specific gravity of aluminum times density of water times the volume of the piston, which is in 2 pi, so pi r square L as written in 1 minus mu v by t into 2 pi rl is 0. So I obtained this by substituting the expression for Fs and expression for mass in this force balance equation. And then if you solve this simple equation, you will get V to be equal to specific gravity of aluminum times density of water, radius g. I forgot a g here. So this is the mass, and the weight is given by mass times gravity. So there is a gravity here into the thickness of the oil film T divided by 2 mu. So this is the expression for the terminal velocity. But again, we are given all these properties The specific gravity for aluminum is 2.64. We know raw water is 1000 kg per meter cube. R is given to be equal to, so the diameter is given, and also the inner diameter of the aluminum piston is given, which is 73 mm. So R is 1 by 2 times 73 mm. So writing it in meters. So radius is this. Acceleration due to gravity is 9.81 meter per second square. The film thickness, again, the if I sketch it again, so the piston diameter is 73 mm, but the tube diameter is 75 mm. So this thickness T is nothing but 1 mm. So this is 10 power minus 3 meters. And for finding out the viscosity of this specific oil, you can just Google it or use use any of the handbooks, and you'll find out that mu for this oil is 0.13 Pascal second at 25 degrees Celsius. So we have the values of all the variables on the right hand side, and if you substitute these in here, you'll find out that V, that is the terminal velocity that the piston will attain, is 3.64 meter per second. So this is the final answer.